Welcome to today's lesson on how the anatomy of the pentadactyl limb provides scientists with evidence for evolution. We will explore the fascinating connections between limb structures in different species and how these similarities support the theory of evolution. In today's lesson, we will study the details of what a pentadactyl limb is and its various forms in different animals. We will examine the evidence from these limb structures that suggest a common ancestor and discuss the implications for our understanding of evolution. So far, you have learned about fossils as key evidence for evolution. Fossils provide snapshots of past life and allow us to piece together the history of different organisms over time. This foundational knowledge of fossils sets the stage for us to explore how living organisms' anatomical features, like the pentadactyl limb, further enforce the principle of evolution. Understanding the anatomy of the pentadactyl limb and its evolutionary significance advances our biological understanding by demonstrating how different species are connected through shared characteristics. It highlights how we can find evidence of a common ancestor and the gradual changes that have occurred over time, reinforcing the broader concepts of evolution. Let's get started. Let's start by understanding what the pentadactyl limb is. A pentadactyl limb is a limb with 5 digits. You can see this type of limb in many different species, including humans, bats, whales, and even lizards. Despite the vastly different functions these limbs perform, their underlying bone structure is strikingly similar. In humans, the pentadactyl limb forms the hand, which is highly adapted for grasping and manipulating objects. In contrast, in bats, the pentadactyl limb has evolved into wings, making them well suited for flight. Whales also possess a pentadactyl limb, but in their case, it is adapted into a flipper, allowing effective swimming. Lizards use their pentadactyl limbs for walking and climbing. So, what do these limbs have in common? Let's break down their bone structure. The humerus is the single long bone at the top. The radius and ulna are 2 parallel bones in the lower section. The carpals is a set of small bones making up what we would call the wrist. The metacarpals are bones that form the main part of the hand. The phalanges are the bones in the fingers, or digits. Whether you're looking at a bat's wing, a whale's flipper, or a human hand, this basic structure is always present, though the size and shape of the individual bones might vary significantly to suit different functions. The question is, why do such different species share this similar bone structure? The concept of evolution provides a compelling explanation. The similarity in bone structure across different species suggests that these diverse organisms all share a common ancestor. This ancestral species possessed a pentadactyl limb, which was passed down to descendant species. Over millions of years, these descendants diversified and adapted their limbs for various functions to survive in different environments. For example, upon close examination, the pentadactyl limbs in fossils similarly show this common structure, reinforcing the idea that mammals, reptiles, and amphibians evolved from a common ancestor with this type of limb. So how has this limb come to differ in use among different species? Adaptive radiation is the process by which organisms diversify rapidly into a multitude of new forms, particularly when a change in the environment makes new resources available and creates new challenges. The pentadactyl limb is a classic example of this process. Different species adapted their limbs in response to different environmental pressures. This led to the wide variety of limb functions we see today, from the flight of bats to the swimming of whales. Studying the pentadactyl limb helps scientists to understand how different species have evolved over time. It provides concrete evidence for the theory of evolution, demonstrating how species can diversify and adapt from a common ancestor over millions of years. When observing the various pentadactyl limbs across species, it becomes clear how natural selection and adaptation work to give rise to the diversity of life. By analysing this shared skeletal framework, scientists can piece together evolutionary lines and establish how different organisms are related, offering us a deeper understanding of the history of life on Earth. In today's lesson, we explored how the pentadactyl, 5-fingered, limb provides strong evidence for evolution. The pentadactyl limb, found in many vertebrates like humans, whales, bats, and lizards, has a shared bone structure despite differing functions and appearances. This common structure suggests that these species evolved from a common ancestor with a pentadactyl limb. Fossil records show how this limb adapted over time to various environments. This concept reinforces evolutionary theory and highlights the interconnectedness of life on Earth. This lesson underscores the importance of comparative anatomy and fossil records in understanding biological evolution.